This presentation takes an introductory look at ideas about ionisation enthalpy. By the end of the presentation, you should understand what's meant by ionisation generally, and specifically what's meant by first ionisation enthalpy, second ionisation enthalpy, third ionisation enthalpy, and so on. And you need to be able to represent the processes that are occurring as chemical equations with state symbols. So let's start by considering what we mean by ionisation in general before we look at the specifics. The word ionisation involves ion, and so it is to do with forming ions, but very specifically it's to do with removing electrons from atoms. Now if we remove electrons from atoms, then we'll end up with positive ions. So an example would be to take sodium, remove an electron, and you get Na+. That very general definition won't get us very far, and we need to get a lot more precise. Now, when we come to talk about the enthalpy change involved in ionisation, we actually think about various different types of ionisation, which get called first ionisation, second ionisation, third ionisation, and so on. We'll start at the beginning, as it seems right to do. So first ionisation enthalpy. We need a very technical definition for this, and it's this. So the first ionisation enthalpy is defined as the energy required to remove one electron from each atom in 1 mole of atoms in the gas state. There's an awful lot in there, so it being an enthalpy change is to do with the energy involved. Now, just look a little bit more closely. So what we're doing is we're taking 1 electron from each atom, and we're talking about a mole of atoms, and it has to be in the gas state. You need all of those ideas in your definition. There are other ways of saying it. So for instance, you could say it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, which works out at the same thing. We need a symbol for the first ionisation enthalpy as well, and you see it here. So it's delta H, as with any enthalpy change, then a lowercase I standing for ionisation, and then in brackets 1, which means the first ionisation enthalpy. As with all the other enthalpy changes we've considered, the units are kilojoules per mole. And we can actually predict for these ionisation enthalpies that they're going to be endothermic, because we're going to have to be supplying energy to pull electrons away from the attracting nucleus. And so therefore we'll have a positive value for these first ionisation enthalpies. As well as being able to write a definition for what we mean by first ionisation enthalpy generally, we need to be able to write chemical equations to represent what's actually going on for any given element. Now, it's very important to note here that first ionisation enthalpy is not a representation of what actually happens for any given element when it forms an ion. So don't link it up in your head with, oh, this is in group 2, so it'll lose 2 outer shell electrons. This is a fairly theoretical idea of simply pulling off electrons from an atom. So don't get confused or worried by what you think that element actually does do when it forms an ion in a chemical reaction. As an example, let's look at nitrogen then. So the first ionisation enthalpy of nitrogen, and if we work through the definition, we're going to have atoms in the gas state, and 1 mole of them, so we don't need any balancing coefficient in front of it. And then we're going to take an electron off to make a 1+ ion in the gas state, therefore. Now we have to show the electron that's been lost, and so we write that separately on the right hand side as +E-. So in a way what this represents is that we started with a nitrogen atom in the gas state, and at the end of the process we've now got a nitrogen plus ion in the gas state and an electron which is now separate from it. Another example then, calcium. Why don't you have a go at this one yourself? Pause the video, write out the equation then that would represent the process that takes place for the first ionisation of calcium. Hopefully you got this. The pattern matches the nitrogen one exactly. we're just changing the symbol of the element. And that's going to be the case for all of these first ionisation enthalpies. They'll always follow this pattern, just simply the relevant element symbol. A final one then, iodine. Have another go. Make sure you can do this. And we're coming up with exactly the same pattern again. Just to reinforce the point, nitrogen, of course, is a non-metal, so it tends to gain electrons when it makes ions naturally in chemical reactions. So this is not something that we would expect nitrogen to do in a chemical reaction. It's a specific measurement that we might make for nitrogen, the enthalpy change when we remove one electron from it. So that was first ionisation enthalpy. What about second ionisation enthalpy? And we need to be very careful here. Let me just give you a warning. There's an easy trap to fall into that you think that if first ionisation enthalpy was removing one electron, then second ionisation enthalpy is simply removing two electrons from an atom. Well, that's not the case. So look carefully at this definition. Second ionisation enthalpy is the energy required to remove one electron from each ion in a mole of 1+ ions in the gas state. So actually what we're doing here is not removing two electrons, we're removing a second electron. The first ionisation enthalpy, measuring what happens when you remove the first electron from the outer shell, and then second ionisation is when you then carry on to remove one more electron, the second electron that you're taking away. So you're going to be starting with a 1+ ion and taking an electron away, which is then therefore produce a 2+ ion. Again, we need to be able to write chemical equations to represent the change involved when we're talking about second ionisation enthalpy of an element. So we'll consider magnesium and its second ionisation. So working through the definition, again, we're going to be starting this time not with a magnesium atom, but already with an Mg+ ion. It's already lost one electron, and it's going to be in the gas state, according to the definition. So when we remove an electron from that, we'll end up with an Mg2+ ion in the gas state. And again, we represent the electron that's been lost as +E- on the right-hand side. So we can do this for any element. Bromine, for instance. Why don't you pause the video and just make sure that you've got this. Write out an equation to represent the second ionisation of bromine. And hopefully you'd have written this. Again, note the pattern matches exactly. So for any second ionisation enthalpy, you're always going to follow this pattern from a 1+ ion in the gas state to a 2+ ion in the gas state plus an electron. If you followed along so far, you hopefully can see, on this basis, you can write any old ionisation enthalpy for any element. So if we jump straight to the 6th ionisation enthalpy and we pick chlorine as an example, we're going to be removing a 6th electron. And so we'll be starting with a 5+ ion in the gas state and going to a 6+ ion in the gas state plus the electron that's been lost, written there on the right-hand side. So if you want a sort of easy check system to make sure you're getting this right, just note that whatever number the ionisation enthalpy is, that should be the charge of the positive product ion. So the 6th ionisation enthalpy produces a 6+ ion, and on the reactant side it'll be simply a positive ion with one less charge than that. So for the 6th ionisation enthalpy we're starting with a 5+ ion. Here's a couple of questions then to make sure that you've followed along so far. Spot the errors in the following two equations. So we've got the second ionisation enthalpy for phosphorus and then the first ionisation enthalpy for potassium. There's something definitely wrong with each of those equations, so see if you can spot what it is and therefore what the equation should actually be. Well, hopefully for the phosphorus you recognise that if it's the second ionisation enthalpy, we should be starting with P+ and going to P2+ with a loss of just one electron. For the potassium, we've got a couple of problems here. Didn't include the state symbols, so you need K gas and K+ gas, and also the electron lost shouldn't be subtracted on the left. Conventionally we write it as being present on the right as +E-.